Hey guys, welcome back to another video. So in this video, we're going to be talking about the laws of thermodynamics. There are technically three laws of thermodynamics, but we're gonna talk about a precursor called the zeroth law, and it's related to thermal equilibrium. So essentially, what thermal equilibrium is let's say you have that's not good. You have a mug of water, but they're at different temperatures, right? So let's say this is at 100 degrees Celsius, and this is like 70, and they're the same amount of water in each, and then you put them in a bigger beaker, right? When you mix them, well, they're not at 100 degrees or 70 degrees. It's somewhere at 85 degrees. So the temperature is in equilibrium. So we can apply the same concept to the zeroth law. The zeroth law says that if A is in equilibrium to B, sorry, that's 85 degrees. If A is in equilibrium to B and C is equilibrium with B, then A and C are in equilibrium. Well, this is just, using our common sense, but we have to sort of formalize this in a law, and that's the zeroth law. The first law of thermodynamics is conservation of energy. So we've talked about this a lot, but I think it's important to, just reinforce this idea. So the conservation of energy states that energy cannot be created It can't be created or destroyed. It just changes form. So it can't be created or destroyed. It just changes. So, good examples of this are, as I've said before, you're dropping a rock in the air. When it's at its height, like when you're dropping it at its height, right? You're dropping it at the ground. If you're dropping it at its height, all of it is in potential energy, mgh. But as you drop it more and more, as it falls more and more of that same energy is transforming into kinetic energy. So at this point, if you look at the energy composition, half of it is kinetic energy from the falling, and half of it is potential energy. So energy isn't being created, it's just changing form. So it's still one. The second law of thermodynamics is related to increasing entropy. Now, personally, this law was always harder to understand, so I'm gonna try to break it down as best as I can. So, in a quantifiable sort of way, this law basically says that the change in entropy of your system plus your change of entropy in your surroundings is always positive. So what this says is, in an isolated system of any kind, your entropy is always increasing, because these are deltas. So what entropy is, a good way to understand it physically is it's the disorder we see in our universe. And an analogy I like to have for this sort of phenomenon happening is, let's say you have a room. You have all these things in your room, right? Like, let's say you have your bed sheets, your pillows, just, I don't know, like books or something. So there is exactly one spot for each thing. So your books go on your bookshelf, your pillows have to be lined up a certain way. There are more ways for it to not be in its correct position than there are correct positions. So if you literally move your pillow like 2 inches, then it's dirty. It's disorder. So basically, at a probability, everything over time will be more disorderly. And even if you decide to clean it, sure, your entropy of your system will decrease, but the effort you put in cleaning it from the surroundings will exceed the entropy decreased. So anyways, your entropy will end up increasing. The last law of thermodynamics is something related to zero entropy. So in the real world, we really haven't experienced zero entropy. And this law basically states that in a certain really specific case, zero entropy is supposed to be reached. It's theorized. So sort of the requirements for zero entropy is it has to be at absolute zero. And in absolute zero, apparently all like motion of molecules is supposed to stop. Oh, oops, that's not what I meant. Absolute zero. And the second requirement is it has to be a perfect crystal. So a perfect crystal is basically a crystal with sort of no dislocations. So normally in a crystal lattice, we'll talk about this more in the next few units, but a crystal lattice will have pluses and minuses. Oops, that's a really bad drawing. So it'll just be overlapping sort of lattices like this. So this is actually a perfect crystal, right? So everything is supposed to be where it's supposed to be. But most crystals that we see aren't like this. Some crystals will have sort of a misalignment like that, where it's supposed to be here, but it shifts that way. Not everything in the real world is perfect. So for zero entropy to happen, it needs to be at absolute zero, and it needs to be a perfect crystal. So that's the 3 laws of thermodynamics, technically 4. I hope you guys liked it. I'll see you guys in the next video.